In the next couple of videos, we're going to work with exponential functions that have a base of e, which is called the natural exponential function. The natural exponential function. So the key word here is natural. And that's when you have a natural base, and that natural base is e. And e is approximately the value of 2.718. And it does keep going, and it's an irrational number. Just like pi is an irrational number that doesn't ever change. E is also an irrational number. And pi comes from the circumference of a circle divided by the denominator. E comes from being the horizontal asymptote of the function 1 plus 1 over x raised to the x power. So as x approaches infinity, f of x approaches the value of e, which is pretty interesting. So you've got this graph here, and this would be a horizontal asymptote at y equals e, which is approximately 2.718. I always go up 3 decimal places, starting at this level of math and higher. Yeah, so you'll as x gets really, really big, you'll have that function that approaches that asymptote of e. So if we practice using e in our calculator, let's just make sure that we know how to put e into our calculator. E will be found as the second or sometimes the shift button of the natural log button, ln for natural log. So e raised to the negative 2 power. Let's make sure that you can put that into your calculator. So go ahead and give yourself a chance to put that in. And if you need to press pause, go ahead and press pause. And then press play when you're ready to look at the answer. Okay, so hopefully you had a chance to not be a follower, to actually put this into your calculator and confirm that you are able to get these values. Let's do e to the negative 1, e to the 0, and then I'm going to start e to the first, e to the second. So I'm going to drop that upper caret, e to the negative 1. So I would press pause, try doing those 4, and then come on back and check your answers. So e to the negative 1 is 0.368. E to the 0 power is 1, because any base raised to the 0 power is 1. E to the first power would be the value of e, which is about 2.718. And then e squared is 7.389-ish. 7.389-ish. So when we put this into a graph, okay, so I've got this graph. If I want to graph f of x equals e to the x, if I put a negative 2 in, I'm going to get something like 0.1-ish, 135-ish. If I put a negative 1 in, I get a little bit higher of an output, 0.3-ish. If I put a 0 in, I get a 1-ish, not 1-ish, 1. If I put a 1 in, I get between 2 and 3, 2.718-ish. And 4, 5, 6, 7, 8. So this is what I do right here. When I put a 2 in, I know that I'm going to get out between 7 and 8. So I don't really remember e squared, but I remember it's between 7 and 8, because this is going to be a parent function that we're going to want to have memorized pretty quickly. So the points I remember are 0, 1, 1, 2.7-ish, and 2, 7.3-ish. Like, I'm not even rounding because I just put between 7 and 8. Okay. So that right there is another parent function that I'm going to go backwards here, that we can transform. We can reflect it over the x-axis, over the y-axis. We can translate it down several units. We can translate it left and right, up. So just like y equals 2 to the x is a parent function that we graphed here, y equals 2 to the x. But then in our examples, we worked with y equals 3 to the x. We'll now be able to work with y equals e to the x. Now, e is important. It's also called the banker's constant. And that's because we use it when we're working with money. So let me show you this formula, compound interest. Compound interest formula, and you may be familiar with this formula. It's A equals P times the quantity, 1 plus R over N raised to the NT power. And there are no X's and Y's, but there are still inputs and outputs. So 2 of these letters are going to be variables, and the others will be what we call parameters. So our 2 variables, I'm going to highlight them. Our output is going to be the A, and our input is going to be the time. And there's a letter that I'm missing right here, and it's P. So that's our input and our output. So this is our input. Time is our input, and the amount is our output. So A stands for our ending value. So it's our ending dollar value. Ending dollar value after T number of years. I don't think I need a comma there. After T years. And T is the number of years the balance earns interest. So the rest of these letters, I'm going to write this in red, the rest of these letters are going to be called parameters. So these are things that we need to know before we create our function. So these are things that the word problem is going to give us to fill in so that we can create that function. So N is going to stand for the number of times the balance or the interest is compounded interest. Number of times interest. I don't want to say interest. The number of times the account is compounded, that's what I want to say, per year. The number of times the account is compounded per year. That means how many times is the bank going to look at your account and calculate interest for you. R is the annual interest rate. So the annual interest rate. And then P is the initial dollar value. So the initial dollar value that you invest. So here in our first example, Joe invests $5,000. So this right here invests $5,000. That's our P value. So I'm going to write P equals 5,000. So that's one value of a parameter. And he invests that at an annual percentage rate of 7%. So R is equal to 0.07. We're going to take that percentage and we're going to make it a decimal. Now, if the bank, so I'm going to put, that's R, if the bank compounds quarterly, that tells you how many times they're going to look at your account each year. So quarterly, there's 4 quarters in a year. That means that N equals 4. How much does he have after 2 years? So before I go into the how much does he have after 2 years, this 2 years is an input. So this right here is my time, which is an input. So before I put that value in, I'm going to actually create the function. So the function, and if you write this function down a few times, you'll have it memorized, which is a function, this is a formula that you're going to need to have memorized. So it would be helpful to write the formula down a few times so that you can get it memorized. The end amount is my output. The principal amount is a parameter. 1 plus the interest rate of 0.07 divided by 4 raised to the 4 times t power. So this right here is our function. It has an input and an output. Now that we have the function, we can put in time equals 2. So we'll have A equals 5,000 times 1 plus 0.07 divided by 4 raised to the 4 times 2 years. Now, before we get anxious and put this into our calculator, let's look at this exponent. In 2 years' time, the bank is going to compound the account 8 times. So 4 times per year, right? 4 times per year means 8 times in 2 years. And that's why the exponent is 8. So we put this into our calculator, and I'll let you practice putting this into your calculator and making sure that press pause, or if you just don't want to be surprised and you want to make sure that you have the right number, $5,744.41. It's a lot of 4s right there. $5,744.41 after 2 years. So that's not too bad. Deposit $5,000 and 2 years later, you'll have $744 that you earned in interest. And compound interest is when your interest earns interest. So the fact that they are not just evaluating the bank, the bank is not just evaluating your account at the end of 2 years. They are evaluating the account quarterly. That means after the first quarter, you're going to have no longer $5,000. You're going to have $5,000 plus some interest that you earned, right? And then the second quarter, that interest that you earned is going to earn more interest because they're going to take that $5,000 plus interest and it's going to earn interest. And then the third quarter, so on and so forth. All of this gets evaluated and it earns interest on top of its interest. Now, continuously means not quarters, but continuously means when they're looking at your account daily. Not daily, continuously, all the time. Daily, let's talk about that first. Monthly, N would equal 12. Daily, N would equal 365. Continuously is even more so than daily. You don't have to wait until the end of the day. It's continuously earning interest. And that is when we use the value of E. So we have A equals P times E raised to the RT power. Again, our input is our time in years. The output is the end value, A, after T years. And then our parameters, the values that we're going to be given in the problem will be the initial investment and the interest rate. And then of course E is a constant. That's a constant. Its value never changes. It's about 2.718. So here we have Michelle invests $25,000 at a rate of 4% compounded continuously. So the investment of $25,000 is our principal. A rate of 4% is the R value. That would be 0.04. And then compounded continuously, that tells us that we're using the formula A equals P. I'm going to write this a little bit better for those of you that are not maybe as familiar with it as you'll become familiar. A equals P times E, and then E is raised to the RT power. So you're going to take E, raise it to the RT power, and then multiply that result by P. So we'll have our function. Let's talk about our function. The function is going to be the output A equals 25,000 times E raised to the 0.04 T power. And I put a little hook on the bottom of my T so it doesn't look like a plus sign. Now they ask how much did she earn after 5 years? So that's where we put in the value of 5 in for T, E raised to the 0.04 times 5 power. So we're going to need to make sure that we have all of that exponent in our calculator. So I'm going to show you. Some of you are going right to your calculator, which is a good thing. You're going to hit 25,000, and then you'll hit the times button. That means times. And then you'll bring up the E button. And then you'll hit the upper caret, if it doesn't already show you the upper caret. And then in parentheses, you need to make sure that all of 0.04 times 5 is part of that exponent. So I put parentheses around that multiplication, that product, to ensure that all of 0.04 times 5 is in the exponent. Some of the calculators now show you what's in the exponent, so it's not that much of an issue, but in case your calculator does not show you what's in the exponent, and it shows you the upper caret, that's it right there. If it shows you the upper caret and doesn't show you that it's being raised, but instead shows you this character, then you need the parentheses around the 0.04 times 5. And then when I put that in my calculator, I get approximately, I've got a dollar amount, $30,535.07. Now that's the end dollar amount, right? So that's the end dollar value of the account after 5 years. It says how much did she earn? Well, if she initially put in the $25,000, you'd have to subtract out that principal value because she didn't earn the principal. That's what she deposited. And she would have earned $5,535.07. So that's how much she earned by placing her money in an account that was compounded continuously for 5 years. And that concludes our notes. So we've got a little bit, what did we do here? So we continued our graphing a little bit using a new base, E. It's probably not the first time that you've seen E, but it was hopefully a nice little review. And then we worked with the compound interest. And this might have been a little bit of review as well. There were two main formulas that we worked with. We worked with compound interest, A equals P times the quantity, 1 plus R over N raised to the NT power. That right there works when you're compounding monthly or daily, continuously, quarterly. Not continuously. Continuously is when we have PERT. So monthly, daily, quarterly are typically the types of compounding that we do per year, whereas the continuously is using A equals P times E raised to the RT power. And the E value is the banker's constant because it really does have a link back to this right here. So if we look at this right here, 1 plus 1 over x raised to the x power, and we're talking about x as it approaches infinity. That means how many times are we compounding per year? An infinite number. So as x gets really, 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 really big, this value right here approaches E. And that's why this is replaced with E. Pretty cool. Pretty cool stuff there. So probably not a bad idea for you to maybe think about that, or just, tuck it away somewhere and say, I remember that it came from somewhere. It's not just a formula that came out of nowhere. It actually does come from somewhere. So thanks for listening, and get some practice with those word problems. These are some of the simpler ones to get us warmed up. We'll be doing all sorts of problems with logarithms and word problems with money once we get to our logarithms lesson.